Hello again there everyone. I hope you're all doing well. This is Chemistry Grade 12. The topic we are continuing is entropy. As it was in the last class, I hope you've got your pen or pencils and a notebook to make short notes. And don't forget a calculator as well, since we will be seeing some calculations later on today. Now, do you remember what we saw in the last class? Let's try and recall some of the concepts that we saw during that class, shall we? Alright, last time we saw an introduction to entropy. We used a capital S to denote entropy, and then we also had a look at some definitions and several examples to explain what entropy is. We defined it as the random dispersal of molecules and energy quanta between molecules and between the molecules and surroundings. We also had a look at the terms system, which is the species involved in the reaction, and surroundings, which is everything else. Furthermore, we said that when disorder increases, entropy increases. We saw this through the entropy versus temperature graph. I hope you remember that one, where we saw that entropy increased with the change of state from solid to liquid to gas. This we will further explore in today's lesson as well. So let's first have a look at the objectives for today's lesson. It is to understand why entropy changes occur during change of state, or dissolving of a solid ionic lattice, or when there is a change in the number of moles from reactants to products in reactions. And also we will see how to calculate the entropy change of the system given the standard entropy values of reactants and products. So let's see what we have in store for today. Okay, so do you remember this slide from the previous lesson? It shows water in three different states, and we saw that entropy increases when there is a change of state. In other words, entropy values depend on temperature and physical state. You can see very clearly on this slide as well. See the values, they are very different for each physical state of water. And moreover, notice how it is changing. With more disorder, the value is increasing. That is, for the gas, you can see it has the highest entropy value. In other words, the greater the disorder, the higher the entropy, the more positive the entropy value becomes. In fact, the gaseous state has got the highest or the most positive value of 188.7 joules per Kelvin per mole. This will be an important part when we get to calculations. So before we go into calculations, let's have a look at some instances where entropy changes and explore what you would expect the value of entropy to be like. Here we go then. These are some ways in which the entropy changes. Changes when solids melt or liquids boil, solid dissolves in water, or when the number of moles increases from reactants to products, or even when the number of gas molecules changes. As you know, gases have higher entropy compared to solids or even liquids. Now we will see all of these in more detail. Let's do that. Firstly, entropy increases when solids melt or when liquids boil. Now this is one graph that you have seen in the previous lesson as well, and you can clearly see how entropy is affected by change in temperature and hence physical state. So what is the reason for this entropy change with the change of physical state? If you look at it at a molecular level, you see energy of the particles increases, and at melting or boiling temperature, the particles break away from each other and move further apart. This again you can clearly see on the slide there as well. This increases disorder and therefore entropy as well. Or you can even say that change in entropy is positive. Second one is where entropy changes when solids dissolve in water to form aqueous ions. Here the particles which were once in fixed positions in the solid state are now free to move around in solution. As you can see it from the diagram there, the orange circles represent the solid, and once it dissolves in water, that is the blue circles, you can see the interaction between the two there. You can see on the second diagram there, or rather the second box, the orange particles, or now ions, surrounded by water molecules, are able to move much more freely. If you can have a look at a second diagram here, and imagine that solid as sodium chloride, for example, an ionic solid. The sodium ions as the circles with the positive charge, the yellow ones, and the chloride ions, the circles with the negative charge, the green ones. You see how they interact with water molecules and how they are able to move much more freely than in the solid state. Again, you can see that disorder increases from solid to aqueous ions, or change in entropy is positive. Keep in mind that in dissolving a solid in water, there are other processes that involve energy changes, namely lattice enthalpy and hydration enthalpy. However, we will not explore them here, but we will see them a bit later on in this topic. Third one is when you have the number of gas molecules changing in a reaction, how does that affect the entropy? We already know that entropy of a gas with its freely moving particles is higher than the entropy of corresponding solids or liquids. Take this endothermic reaction for example, where ethanoic acid is reacting with ammonium carbonate and bubbles of a gas are produced, which you can clearly see is carbon dioxide gas. In this case, the particles are well ordered in the solid reactant. However, the disorder increases going from reactants to product because a solution is formed and especially a gas is formed. So entropy increases during this reaction, which means again you will expect a positive entropy value for the reaction. Or take this exothermic reaction of magnesium ribbon burning in air. As you can see, a gas reacts to form a solid, which means this time you can expect the entropy of the system to decrease because solids have considerably more order than gases, which further means that we would expect a negative entropy value this time around. Unlike the previous examples where we expected a positive value because entropy was increasing, this time we are expecting a negative value because this reaction is going from a highly disordered state to a very ordered one. The fourth one is the one where we have the change in the number of moles affecting the change in entropy. When the number of moles increases, automatically the number of particles, that is atoms, molecules or ions, increases. Hence the number of ways that the particles can be arranged will also increase, therefore entropy increases. But how do we check this? By looking at an equation. This is how we do it. To work out if the entropy increases or not, what we do here is we check the number of moles on both sides, that is on the reactants and product side. So let's count the number of moles on both sides. Let's start with the reactants. Check the number of moles on each species there. As you can see, 2 moles of ammonium chloride and then we have hydrated barium hydroxide, 1 mole. That gives you a total of 3 moles of reactants. Do the same on the product side as well. Can you count and check it out? Yep, if you've got 11, that's right. The number of moles of products you have got here is 11. And as you can see, there's an increase in the number of moles from reactants to products, which means more particles, more disorder, and therefore entropy increases. So there you have it, the several ways in which entropy can be affected. Whether you have change in physical states in terms of solids melting or liquids boiling or solids dissolving to form aqueous ions, or when you have gas molecules produced, which will definitely increase the entropy, or you have number of moles changing from reactants to products. However, it is very important to note that in all of these examples we have taken here, we are only talking about the reaction mixture or the species involved in the reaction, which means we are only talking about the entropy of the system and how that is affected or how that is changing. So when you are answering questions and explaining reactions regarding entropy of the system, it is essential that you observe the reaction or equation carefully. That is, to see if there is a change in the physical state or change in the number of moles or if a gas has been produced or not. This will be your justification when you are answering questions based on entropy of the system. So, shall we try some examples and see how we will approach such questions? Alright, so are you ready for the question? Suggest whether the following processes involve an increase or decrease in the entropy of the system and explain your answers. Let's first understand the question. There are two parts to it. Firstly, to say how entropy changes, increase or decrease, that is, and then to explain why you are saying so. The command word used in the question is explain. So it's important to note that across IAS or IAL science qualifications in the assessments, this means it requires a justification. The answer must contain some form of reasoning or justification, and it could even be mathematical explanations. However, keep in mind that if they do ask specifically to not include any calculations, you must give your reasoning without the calculation. So let's have a look at the first one here. Right, magnesium chloride, solid, reacting with water, that's the aqueous symbol there, forming magnesium and chloride ions. So what do you think? Will the entropy increase or decrease? If so, why? Now here's a bit of a help for you here. Several ways in which it could increase or decrease. What do you see here? Do you see a change of physical state, or a solid dissolving, a gas being produced, or number of moles increasing? Well, I'll go with solids dissolving. Yes, there is a change of physical state, and yes, there's a change in the number of moles as well. So you see, you could have more than one reasoning for one example as well. I'll just go with the solids dissolving in this case, which means would the entropy increase or decrease here? It should definitely increase because there's a change of state from solid to aqueous science, as we have just figured out. And as you know that in solids the particles are in fixed positions with orderly arrangement, and when they are dissolved the particles break free from their positions. Hence particles will have more movement and therefore more disorder, higher entropy, which means we will expect a positive entropy value for this reaction. Okay, so we've got number 2 with sodium solid and chlorine gas reacting with sodium chloride solid forming. Would the entropy increase or decrease? Here's your clue box. Which one would you choose here? If you have said entropy decreases because there is a change of physical state, you are right. Entropy should decrease as a solid is formed from a gas, and gases will have particles more randomly arranged than in solid, which means less disorder and therefore decrease in entropy, and we would expect a negative value going from reactants to products in this reaction. Alright, the third one, we've got two gases reacting and forming two gases. Okay, so what do you think? Would the entropy increase or decrease? And what would be your justification? Well, if you have said there's a change of physical state, you will definitely be wrong. Here we can't really talk about the change in the physical state, as they are all gases. So let's have a look at the number of particles on both sides of the reaction, and that would be your justification. If you look at the number of reactants to products, you see that it's 6:7. Products, you have more number of moles on that side, isn't it? So there are more particles on the product side, which means there will be more ways of arranging the particles on the product side, hence increase in the entropy, therefore a positive value for the entropy as well. Okay, so we've come to the fourth example. Here we have hydrated crystals of copper 2 sulfate decompose into form anhydrous copper 2 sulfate and water. What do you think? You have your clue box on the side. Which one would you choose and how would the entropy change? Well, similar to the previous example, we can choose the number of moles, count the number of moles of reactants to products, and you see it's 1:6. Since you have more products than reactants, there will be more ways of arranging the particles or energy quanta, which eventually means there will be an increase in the entropy of the system, which means we will expect a positive value for our entropy as well. I hope you've got some practice in figuring out how to go about answering such questions with the help of these 4 examples. So keep in mind, whenever you have to answer questions on entropy of the system without doing a calculation, fall back to these points for justification. That is, when there is a change of physical state from solid to liquid to gas, entropy will increase. Or when you have a solid dissolving to form aqueous ions, entropy will increase. Or when you have a gas being produced, or when you have number of particles increasing, all these will lead to an increase in the entropy, which means you would also expect a positive value for your entropy as well. Now let's try another way of working out what happens to the entropy of the system, but this time in terms of numbers, and see what we have just said about positive or negative entropy values in our calculations. This is where we will see the first calculations. Right. To calculate entropy change of the system, this is the expression we are going to use. Delta S system is equal to the sum of the molar entropies of the products minus that of the reactants. The S represents entropy and the sigma symbol represents the sum of, or you will be adding up the values. The standard entropy refers to the entropy of a substance at standard temperature and pressure, which is 298 Kelvin and 100 kilopascals. Don't worry about the standard entropy values because they will be given in the question. However, this is the first formula that you have to remember in this topic's calculation, as it will not be given in the question or in your exams. Okay, so are you ready for our first calculation example? Here we go. Calculate the delta S system using the values given in the table for the following reaction. So you've got calcium carbonate decomposing to form calcium oxide and carbon dioxide. You can also see the values are already given. Always check if the equation is balanced or not. As you can see, it's a 1:1:1 reaction in this case. Now, before you rush into doing the calculation, can you tell me if the entropy will increase or decrease by just looking at the equation? Now, this will be based on your previous examples of today. Therefore, what would be the expected sign of the entropy value as well? What do you think? Think of that clue box which we tried with the earlier examples. Well, if you had said it should increase, that is, entropy should increase because you have a gas being produced, therefore more disorder, you are absolutely right. Which means you should also expect a positive value for entropy change of the system. Because when you have entropy increasing, remember, we expect a positive value. All right, now let's work out the calculation and see if what we have predicted here is true or not, whether we get a positive value or not. Are you ready? Okay, so our first step will be to write the expression. Remember, this is one expression that you have to keep in mind, that you have to remember by heart. Okay, delta S system is equal to the sum of the entropies of products minus that of the reactants. Simply substitute to the formula the products value and the reactants value. As you can see, we have 2 products, so you will need 2 values to be substituted and just 1 reactant. So you should have something similar to this expression that I've got. I've just expanded that. The entropies of calcium oxide and carbon dioxide are added together minus that of the reactant, which is calcium carbonate in this case. If you put the values or substitute the values to the same expression, you should have something similar to this. What is the answer you've got? Is it 160.4? You should have got a positive value. But what's very important here is that you will also need to write that plus sign here, because The plus sign actually denotes something. It denotes or it tells us that there was an increase in the entropy change of the system. Remember, we predicted that we would expect the entropy to increase. So that plus sign is important in telling us that it has increased. And don't forget the units as well. It should be joules per Kelvin per mole. So whenever you write down the final answer for the entropy change of the system, please make sure you write the sign and units along with the answer you've got. So you were right, I guess, if you had said positive value, because yep, we have got a positive value here in our first calculation. Ready to try another one? Okay, so we have example 2, nitrogen and hydrogen reacting to form ammonia gas. Again, before calculating, what would you expect here? Would the entropy increase or decrease? What would be the expected sign of the value? What do you think? Well, if you have said negative, then you are correct this time. As the number of gas particles are decreasing, entropy will decrease. Hence, a negative answer will be expected. So, shall we try this again and see if this holds true again? Okay, so what is our first step? To write the expression. Okay, now simply substitute it to the expression just like we did in the previous example. However, notice that unlike the previous example, in this one we don't have all 1 mole species. It's in fact 1:3:2. So please take that into consideration when you are doing the substitution, which means you should have something like this for your expression. 2 moles of ammonia taken into consideration minus that of the reactants, 1 mole of nitrogen and 3 moles of hydrogen. So when you are putting the values and substituting it, you have to take those into consideration. We did not do that in the previous example because it was all 1 mole. I hope that's very clear. Alright, so what's the answer here? Your final answer should be negative 198.8. Don't forget the units, joules per Kelvin per mole. So was this what we expected? Yep, we did. We did say it should be negative and it is indeed negative, the value. Well done. So when you give the final answer again, don't forget the units and don't forget the sign as well. Shall we try one more? All right, here we go. Okay, third and final example for today's lesson. Sodium reacting with chlorine, forming sodium chloride. Again, before calculating, what would you expect here? A positive entropy value or a negative one? You should be really good at predicting the values now, isn't it? With all the practice you've got. Right, it should be negative because it's going from a gas to a solid here. So let's work out the calculations and see if what we have predicted here is true or not. Okay, so our first step should be, remember the expression. Now simply substitute the values just like we saw in the previous 2 examples. Don't forget to consider the number of moles here. You've got half chlorine. Okay, so if you consider that, your expression should be something similar to that you see on the slide there. I hope you are all able to follow the steps. Your final answer should be negative 61.6. Don't forget the units, joules per Kelvin per mole. Now, was this what we expected or predicted? Yes, we did say it should be negative because the reaction goes from a gas to a solid, and we indeed have a negative value. Well done. This reaction of sodium and chlorine to form sodium chloride is an exothermic process that involved a decrease in entropy of the system, as you can see in our calculation. Now, it might be interesting to know that this is a chemical reaction that definitely does occur even though the entropy of the system is decreasing. So my question for you here today is, listen very carefully, how can a change in which there is a decrease in entropy of the system still be possible? Or how can a change in which there is a decrease in entropy of the system be still spontaneous? What does this mean? Something to think about. I'll wrap up today's lesson leaving you with that important question to ponder about for the next day's lesson. So let's recap today's lesson. We saw how entropy can be affected or how it changes, whether it increases or decreases. Entropy increases when there is a change of state from solid to liquid to gas, with gases having the highest entropy values. It also increases when solids dissolve and form aqueous ions, which can move more freely, hence more disorder and entropy. Furthermore, entropy also increases when the number of particles increases, as there will be now more ways of arranging those particles. We can also say that the entropy value will be positive, or more positive or less negative if we are comparing values when entropy increases, and negative when it decreases. And we saw this through the calculation examples. For the calculations, we use the formula delta S system is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. Again, this is one expression that you have to remember for your exams because it's not one that will be given. But keep in mind your entropy values will be given in the question. When doing the calculations, you must include units and the sign for the final answer. It is also important to note that we have only talked about entropy change of the system. And even though we took examples where we saw reactions in which energy was released or absorbed from the surroundings, we have not seen the details of how it or enthalpy is related to entropy in much detail. Now that is also a clue to the question I posed early on. Hope you will be able to come up with some answers for the next lesson and we shall compare our answers then. Thank you all for joining in for the lesson. Until next time, stay safe and have a good day.